This is FE Peer Review. The date is the 1st of February 2023. Gravitational Anomalies, a bird's eye view. We're not going to be getting technical in this video. I'm just going to touch on a few of the big picture points that some people may not have thought of or might have some questions about. I got this idea from a video that Mr. Sensible put out a few days back. It was a conversation between him and Flatzoid, and you all might enjoy it if you haven't watched it already. I didn't watch, I have to admit, the entire 3 hours and 20 minutes. I was there for the live stream for about the first half, and then it got late. But it was a lot of fun while it lasted. So there was a question in one of the comments, and that's what I'm going to address here. John Davies asked, air pressure varies all the time, so why does this not affect weight? And this answer of mine is going to cover that point. It does. But if you look at the math, you'll see that the effect is so incredibly small that it's practically immeasurable, especially in the face of other variables which also cause changes in the gravitational field. For example, if you start at sea level and climb to the top of a mountain, there are at least 3 separate variables causing gravity to change. Number 1 is air pressure. There is the air pressure differential. Less air pressure at higher altitudes would cause less buoyancy. Therefore, people would get heavier at higher altitudes. Let's take a quick peek at the buoyancy equation. The buoyant force is the fluid density, that would be the atmosphere, acceleration due to gravity, and the volume. So the fluid density is the issue here, and that's atmospheric density. If we look at atmospheric density, the density of air, we find that it is very small, and yes, it does change, but here's a representative number. I believe this is the figure near ground sea level. 0.0752 pounds per cubic foot, 1.2 kilograms per cubic meter. So that gives you an idea of the scale that we're dealing with compared to the weight of a person. I'm not going to get into the math here and figure out exactly what percentage that changes a person's weight if they go from the sea shore up to the top of Mount Everest. If any of you feel like doing that, you're welcome to in the comments or in another video. But I think it's self-evident looking at that number there that it's a very, very small amount. Now on to the second factor. Newton's gravity equation describes the attraction being in proportion to the square of the distances between the centers of mass of the objects. Therefore, the force decreases as we gain altitude because we are farther from the center of mass of the Earth. This would cause us to get lighter. Now, I once found myself looking at Newton's equation and thought, gee, I wonder, do we get lighter when we climb up to the top of a mountain? It seems like we should, since the centers of mass are getting farther apart. I had that question a few years back, and when I researched it, I found out that, well, yes, quote, in theory, we do, but there is yet a third factor that outweighs that. And so we actually don't. We actually get heavier when we climb to the top of the mountains, despite being farther away from the center of mass. In other words, nature is complicated, something that sometimes goes over the heads of some flat earthers. So, yeah, if you look at Newton's gravitational equation, according to that, we should be getting lighter as we climb to the top of the mountains. However, we'll move on to point number 3 and find out why we don't. Variations in the density of Earth from one location to another causes variances in the gravitational field. The Earth is not a homogeneous object. It's not all one substance. It's all perfectly even everywhere. It's made up of a bunch of stuff, and it's distributed kind of unevenly around the surface and also inside. The interior of the Earth is not a perfectly symmetrical form. It turns out that number 3 is orders of magnitude more powerful than number 1 and also significantly more powerful than number 2. The reason is that high altitude locations are typically composed of high density stone, while low-lying areas such as plains are filled with silt and soil and are thus less dense. There are maps of the globe showing this. Do a Google search for gravitational anomaly map and look at the images. You'll see that most of the high gravity zones are mountain ranges. You might also look up the Schehallien experiment. Here's a page on NASA's website, every globetard's favorite organization, and it has a nice little video here showing gravitational variation across the surface of the Earth. Red being a higher gravitational force and dark blue being a lower gravitational force. So we see mountainous areas. There's the Himalayas right up there. Pause it. There's the Himalayas right there. Deep red. Mountains there. The mountains of Morocco. The ridge, the what do they call it? The Mid-Atlantic Ridge. And there's the Rocky Mountains and the mountain range on the west side of South America. Those are all the highest gravitational zones, and they correlate very well to the mountain ranges. And now a brief look at the Schehallien experiment. This was an experiment conducted in 1774 at a mountain called Schehallien in Scotland. Schehallien happens to be a very consistent, almost perfectly conical shaped mountain. And because of its regular shape, that made it very useful for this particular experiment. What the clever fellows did who were involved in this experiment, I'll look at this diagram here. They went around to one side of the mountain and they held a plumb bob. And sighting along the line of that plumb bob, which gave them vertical for their location, they sighted a particular star and measured the angle from the plumb line to the star. And then they went around to the other side of the mountain and they repeated it on the other side of the mountain. So if the mass of this mountain was enough to influence the gravitational pull on their plumb bob, when they go around to the other side, their plumb bob, instead of being pulled to the left, should be pulled to the right. Now you can kind of picture this diagram reversed and imagine them on the left side of the mountain. They're going to sight along their plumb bob, and then they're going to measure the distance, the angle, to the star, to the same star. And so that's what they did. They took measurements on each side of the mountain, and they found that indeed the mountain was pulling the plumb bob towards it, and measurably. And their purpose in doing this was to measure the density of the Earth, which they succeeded in doing. They did a detailed survey of the mountain, estimating its volume to a very accurate level. And then based on that and their estimate of the mountain's density, they used a bunch of fancy math to come up with the density of the Earth. Now, I'm just mentioning it here because it's a good observation and experiment that shows, that demonstrates that irregularities on the Earth's surface actually do cause gravitational anomalies, as they should if we understand gravity correctly. So apparently we do. Okay, that's all. I just wanted to share those few little thoughts with you. I thought this might be useful to people if they find themselves discussing these kinds of issues. Again, not too technical here, just the big picture. But I hope you enjoyed it. This is FE Peer Review. Wish you all a very nice day. And as you're heading out the door, if you enjoyed this video, you can always click that like button and maybe even subscribe. Okay, bye now. Take care.